Good morning, everyone. Thank you for coming. It's a pleasure to present to you. And I'll go ahead and share my screen. Today's topic is adding value through design thinking. Adding value through design thinking, like you heard before, my name is Patricia Kiro, and I'm an assistant professor at Fitchburg State University. The outline of this presentation will be the introduction, circular economy, future work, and then the conclusion. I'll also take our time to show you 3 tools that we use to quantify the effects of interventions that we made from our architectural lab. So a little about my educational background. I had my BTech in architecture and my MSc in architecture at Rivers State University. And then from August 2017 to December 2021, I did my PhD, my doctoral studies at Texas A&M University, focusing on circular economy and industrial symbiosis using industrial byproducts for architectural interventions. And I'm currently an assistant professor at Fitchburg State University, teaching architectural concentration at the Engineering Technology Department. So today we'll focus on how is architecture and circular economy related. So in this study, we focus on the role of architecture in circular economy, and the studies are conducted in the following areas: how we investigate the product performance, create a methodological frameworks, and then use life cycle analysis to quantify and then show the impacts of this intervention, impacts in terms of economic intervention, economic impacts, environmental impacts, and social impacts. So the history of a circular economy. When we look at this topic, we want to go back, which architect has been interested in this kind of field. So we look at Buckminster Fuller, he's a renowned architect. And in his lifetime, he explored closed ecological systems. And he also proposed an inventory of the world resources, where he figured out that we can quantify the world's resources and then use them efficiently when we know about them. He also coined the words synergetics, so that there will be a network of use of these resources. He was famous for geometric experimentation. We can see the geodesic dome behind him, which he made for an exhibition. Another important person in the history of this is Walter Stahel. Walter Stahel is an architect, and he had a paper in 1982, which was titled The Product Life Factor. He described a model for a closed loop economy, and is more commonly now referred to as a circular economy. So the circular economy in history started out as a closed loop economy, where there will be a loop of resources we use and bring them back to the beginning of that cycle, a closed loop, sort of like a ring. And he says that eco-design is now a corporate strategy to increase long-term profitability, opening numerous new business models, both on the supply side and the demand side. So for circular economy, it is based on 3 principles that are driven by design. We design to eliminate waste and pollution. We design to circulate products and materials at their highest value. And then we also regenerate nature. We find that in the current economy, we take materials from the earth, make products from them, and eventually throw them away as waste. And this is a linear process. So we say we take, we make, and we discard these things. In a circular economy, by contrast, we want to stop waste being produced in the first place. Another important person in the scheme of circular economy is Ellen MacArthur. So we have what we call the Ellen MacArthur Foundation. And here in her website, we look at what she describes, how she describes circular economy. So the circular economy tackles climate change and other global challenges like biodiversity loss, waste, and pollution by decoupling economic activity from the consumption of finite resources. And in 2010, MacArthur launched the Ellen MacArthur Foundation, which promoted efforts aimed at reinventing traditional modes of economic production and consumption. So something about Ellen MacArthur is that she sailed around the world. She's the youngest dame that was made in Britain. And while sailing, she had the idea to pursue the circular economy because of the amount of waste that she saw as she moved around the ocean. So this is a picture of Ellen MacArthur and Walter Stahel. It's very interesting that somebody the idea came up to him in 1982, and then 10 years later, they're working together to improve on this idea. So we have what we call the butterfly diagram. In this butterfly diagram, we have the system shown. On the right, we see that those are machines, mining, manufacturing. On the left, we have the chemical feedstock, the biosphere, biological cycles, while we have the technical cycles on the right. And in this study, we focused on reuse. In the orange box, we see that we have reuse and redistribute. So there are many ways, many approaches that people are using for the circular economy. If you went online and checked existing literature, you'll see a lot of literature on biofuels, you see a lot of literature on recycling. So the argument is that we can also contribute to this discussion of circular economy with our architectural skills in terms of reuse, which is important. So going on to the why reuse, the United States Environmental Protection Agency has a waste management hierarchy. So in this triangle, kind of upside down triangle, you see that they have a source, reduction, and reuse as the most, the suggested solution. And then if you cannot reduce at source or reuse, you move on to recycling or composting. Then you can try energy recovery, and then finally treatment and disposal. So whatever intervention or idea strategies we bring into reuse, as architects will be welcome in saving energy, saving materials, and promoting those closed loops of circular economy. In this chart here, from the data existing in the waste management data from the United States Environmental Protection Agency, we see the amount of material that has been landfilled in yellow, those that are combusted with energy recovery, and those that are recycled. So based on this, we can calculate the amount of material. We have one for metals on the left and one for plastics on the right, to show that reuse would really save the energy that is used in all these processes. So for architectural reuse, we look at the three arms. First, we want to explore, how do we explore in terms of a modular reuse, ecosystem services, and then we want to educate, make the community aware of what circular economy is, what sustainability is, and then how can we improve value by design. On the third factor, we want to reduce water use, reduce virgin material extraction, because when we use these circular materials, as there'll be secondary materials, there won't be the primary virgin material that in these products, and then we'll in turn reduce greenhouse gas emissions. We also have the AIA 2030 challenge, where we want to be able to reduce fossil fuel energy consumption by 70%. That was in 2019. They wanted it to be reduced by 80% in 2020. The 2025 goal is 90%, and then hope to be carbon neutral by 2030. And one of the suggestions for this circularity in the circularity gap report for 2018 and 2019, it says the world is 8.6% circular. The circular economy package established a program of action, and the circularity gap report for 2023 now says 7.2% circular. So we see that circularity is reducing. We need new models, new practices, interventions to make the world more circular. And then we talk about the topic of industrial symbiosis. So from literature, we see that there have been cross-industry networks. This means that industries have been exchanging their waste since in the CE model since the early 2000s. And the CE package explicitly refers to industrial symbiosis as a core strategy to promote circularity. Also, industrial symbiosis involves a waste or byproduct exchange and utility sharing networks among co-located firms. So you find out firms that are in the same location, somebody can exchange their waste products. Let's say some people had steam and other people needed it, so they piped it to save that energy that they were using to produce theirs. So in this study, we first looked at the waste material of steel. And this steel waste is from the automotive industry. The research was funded by General Motors where they have this scrap metal. After cutting out the bodies of cars, we have the scrap metal, and on the right, we can see different shapes of this metal. So we're looking at predictable sizes of metal, predictable sizes of these cut-offs from the metal. How can we reuse them in building facades? How can we use them as a building product? So we looked at 11 predictably sized offal and galvanized sheet metal scrap from General Motors. So this scrap metal is referred to as offal. These materials were brought to the students in Texas A&M University. So the first experience I had with this material was in the class, the students were asked to design products from this material. What material can you replace that is already existing with these offal? So the first group made the offal energy. You can see those fans made from the steel plate. And then we had this radiant scoop, so something for ventilation. And then the third group made a water collector. And then there was a choice cut ceiling. And then another person made the breathable envelope to replace the concrete block wall. Also, we tried to replace, let's say we tried to copy a company called the Alcoa Aluminum Company of America. It's called Alcoa, that's the acronym. And they made aluminum for a lot of work, a lot of projects. So in this case, the owners wanted a building that would represent their identity. And they made these panels for their building from scratch. So you can see the example of one panel, how big it is, see a man there to give us a sense of scale, and then look at the openings. So this building, the emerging opportunities from this engagement with material investigations, informative design process, there was a search for unmatched handwork or finishing. They had field testing. And at the end of the day, they were able to produce these panels that were applied in the Alcoa building in Pittsburgh. So for our own projects, we tried to make a panel using this material and then compare the embodied energy of the panel from Alcoa and the panel from these scrap metal or the offal from General Motors. At the end of the day, we reported it in an inventory of energy consumption. We have the Alcoa panels, and then we call this the faceted metal panel cladding system. So comparing them in terms of their material, the mode of production, the number of units to make that 1 square meter, the area of units required to make this 6 by 12, and then the mass of the material. So one thing about this 6 by 12 is that we have to define different functional units for each product. So since that metal is already a unit of 6 by 12, we try to compare with existing sizes. So the mass of the material, the thickness, the transportation distance from moving the material where you made to where it's being used, struck carbon emission, the virgin material comparison, material carbon emission, and then the costs of new material and also scrap material. Thereafter, you compare them and then lead to an efficiency to see if we cannot compare some things, then we say not applicable. We check with the, and then out here, you can see that the advantage the Alcoa panel had over the faceted metal panel cladding system is that it was in one piece, while we had a lot of cuts in the faceted cladding system. So we're going to talk about life cycle analysis. So in life cycle analysis, it is we want to model the products as properties of the product systems. And these systems are characterized and subdivided into a set of unique processes. And then we have what we call whole building life cycle analysis. That is, we take the whole building and then charts from material extraction up to installation, operational, the maintenance is also involved in that, and then down to demolition of the building. While in the cradle to gate analysis, we're concerned with material extraction up to the installation. So in these studies, we focus on the cradle to gate life cycle analysis because we are talking about the material property. We're talking about the products that made up this building. So under this cradle to gate life cycle analysis, we have the life cycle impact assessment, life cycle interpretation, study goals and scope. the intended audience, functional and declared units, and then the system boundary. So this life cycle interpretation phase of the LCA uses findings of the life cycle inventory to reach conclusions and recommendations about the defined goal and scope. And then we looked at this study to introduce an alternative approach for materials due to the increased practice of storage and landfilling, those that lead to pollution in the society. And then we choose functional units for annual quantity of the products. So this is an example of how we make a system boundary for the product. We look at recycling. We're comparing the reuse to recycling. That's in recycling, they have the processes of pre-washing, separation, grinding, filtration, washing, flotation, drying, sieving, and pyrolysis. While in the case of the reuse, we have design, testing, comparison to prototype, and then assembly. So when we do reuse processes, now in this case, you are proposing a reuse. So find out what is the energy involved in the processes, find out the energy in the existing practice, and then compare it. In this case, we have 3 existing practices: recycling, landfilling, and combustion. So we compare them and see which one has the most impact. And thereafter, we can say, is this of benefit or not? So this study led to some publications. And if we want, by publications from the beginning, from that embodied energy to now, it has led to these papers. And I'll talk about the first 3 up here: the symbiotic circularity in buildings, an alternative path for valorizing sheet metal waste stream as metal building facade, matrix trays from waste to opportunities, and then in situ experimental evaluation of novel modular living wall system for industrial symbiosis. And this was my doctoral thesis. So I'll talk about that part from my presentation. Over here, we can see that these things are put out in the public, and then people that are interested will cite it in their publications. And thereafter, you know that, okay, I'm making an impactful study, and you can see the areas that are leading to, that people are interested in. So the first paper, symbiotic circularity in buildings, we talked about the parts, those cutouts that we got from the cars. So these 11 parts were presented to the students, and we tried to see, the research question was, does design play a role in these energy savings? Is the design significantly, does it have a significant impact on the difference in the energy? Can we put any design and then get any, can we put any design and get the same energy, or are they equal? So for that, we still have that system boundary. And then here we are comparing. So you can see the blue line is for current practice, and then the dotted lines are proposed. So we're saying that this is the distance from the mine that they get these materials, and then they take it to the company, and then they make the products, as against doing the proposed thing where we're taking from the General Motors assembly, the scrap metal, and using it to produce it. And so more details of this can be found in the paper to show how we break it down, compare the 2 designs, and see the answers. We have this design material circularity factor. And so the second paper, in matrix trays from opportunities to waste, because of the first study, which was focused on steel, the company General Motors said, oh, so you worked on the steel. We also have plastic waste. And these trays, matrix trays, are used to transport these integrated circuit chips. Those are used for the car sensors. So when they are taken out of these plastic trays, we have those plastics there. And before, they used to return it to China, but China has put up a policy saying we do not want to take back waste from you. So what happens to these plastic trays? So here we have a picture of the matrix trays in different colors. We have a black one, and then my advisor is holding it to show you, give you a sense of scale. And we had a student competition, how the students handle this, and also they made a prototype of this final product. So basically what happened with this material is there was a student design competition thrown out, and there was prizes were awarded for this. The first prize was this aquaponics, where they make the fish is there, some plants on top, and then the trays are used for it. Somebody made a ceiling, and then some other people use it for storage. And then you can see some people use that as a lamp holder. while other people put it in a living wall, a green wall. And then we also had a student capstone project where they designed a prototype autonomous shading device. And this device has it's designed to go with the movement of the sun, tilt with it. There were motors in this top part. And then we have a simulation of it also in one of the buildings on campus. We also do the system boundary thing where we have the current and the proposed. So the current practice is in blue. We're getting plastics from Precision Industries. We have trays from the integrated circuits coming into General Motors assembly. So we're saying, instead of comparing it now, when it goes to the landfill, what is the distance? Well, when it's going back for recycling, what is the distance, as against using them to make those blinds and draperies. So for this third paper, I'll show it in the slides where I made them, in situ development. So for that, I'll come over here and then so the institute development, I'll talk about it as a case study, and then I'll go on to talk about the methods, the results, and the summary. I'm trying to expand it now. So this paper we talk about, it was published in the Energy and Building Journal, and with all the story, and it was published in 9th September 2021. So this scrap metal was used by the students in landscape department, landscape architecture, construction science, mathematics. It was a collaboration on deciding what to do with it at first, and then getting a final design, choosing the plants. So by the time I came to join the team on this project, they were almost done with fabricating the novel modular living wall system. And we can see the components here supporting the metal frame that is behind it. There's 12-inch cavity airspace between the living wall and the building wall. Behind it, we have a brick surface. Then we have the OFO planter units, we have irrigation systems, and we have multiple emitters. So each planter here has its own drip system, which you can turn off and on. There's engineered soil, and everything in there is Texas native plants. So we're looking at locally sourced plants. So this is a picture of the wall. So the idea was to develop a methodology. How do we have a method to investigate the performance? So what is the performance of this new product? How does it affect the microclimate? So for that, I carried out on-site measurements, life cycle analysis, and then with this on-site measurement, I was able to carry out EnviMet simulation to determine what is the impact of this wall at different seasons. And then that will lead to the outputs, and then results from the life cycle analysis and the EnviMet output will tell us about the material and thermal performance, and then we'll make some conclusions. So here we have parts to define this methodology. So in order to get the data, I had to use this solar meter, the Canon fisheye camera to determine the sky view factor. We have a weather station, Davis weather station. So this gives you the log of the data every 30 minutes, temperature, humidity. And then we have this Vantage Pro that works with the weather station with a logger behind it. So that's what takes the data off there. And then we have the moisture and temperature probes that are stuck in the plants, in the soil. So it gives us the soil moisture and the temperature. And then we have the leaf temperature and wetness sensor. So putting this by the side, it also gives you the readings for the leaf in those planters. So for the sky view factor, it's very important because we cannot compare the behavior, or we want to compare the sun, the temperature. So the sun affects the air temperature. So when you want to compare it, you cannot compare apples to oranges. So this sky view factor tells us how much exposure that surface is receiving, how much exposure that surface has to the sun. And then if you look at the place at the wall, we have the sky view factor as 0.3. From the middle of the courtyard, we have 0.5. And then at the side, we have 0.12. So the idea was to compare the brick wall behind the living wall and then the brick wall at another point, but you have to ensure that they are both facing the same direction, they have the same orientation. So this will help me to compare my figures at the end of the day, because you can see that this is a 32% exposed to the sun, this is 12%. So they will not be treated equally. So this is showing us an elevation of the living wall, where those soil temperature and moisture probes are, because in simulation, the height of the readings is also important. So when we know the heights, when carrying out the simulation, we also put that height into that software so that we can get results that are as accurate as possible. So ground level, we have the probes here at 1.2 and at 1.5. So the variables for this study, we had to check the ambient air temperature, the air temperature layer, the soil temperature, leaf temperature, the relative humidity, and then the solar radiation. So this is kind of what's the science behind the study. What are the flows of energy at the study site? So we have the incoming solar radiation, the reflected solar radiation, terrestrial radiation, convection that has to do with the air, and see that the radiation also goes into the floor by conduction. And then the plants are also, they have evaporation taking place around them. So here we look at the temperature and the climate in that area. So using a software called Climate Consultant, which I'll show us later, we're able to get the temperature range for each month. And you can see that this region is from the weather station that is in that area. So College Station, weather station, and it tells us from January to December, and then the annual averages. So these are used to compare and then to feed. Usually what we use in the simulation is already connected to the weather stations. But if you want to do a more detailed study and you want to see what's happening in this particular location, we use it to study that particular site. So for the simulation, we have this software called the EnviMet, and in the scenarios, what do we do? Scenario 1 is before. So we can see the building before the wall was put in place. So you have this in the simulation where you have this building and surrounding buildings, have this before, do the simulation, and then after, place, they have walls, they have green walls in the software. So place a green wall there, you can see it's green now, and then do the simulation again, and then compare the two of them. So for the results, we will have charts. So these charts were got from we saw the instruments that were used for the experiment. We have the heat stress tracker, we have the solar meter. So this is plotted for different surfaces. What are the temperature differences? We can see where the least temperature is compared to the highest temperature. And then we have the one for the relative humidity, checking the ambient air and then the air layer to see the differences. And then these are the results from the EnviMet simulation. So on this date, February 13, the simulation is done. You see the colors representing the air temperature, the air temperature in front of the wall. So different colors telling us something below 0 Kelvin and above 0.01 Kelvin. And then we have the comparison of the two, so different seasons. So I took measurements of the temperature and other parameters in front of the wall at different seasons. So we're comparing them that way with simulation. So comparison for 16/8/2019 and 16/8/2019, that is before and after scenarios. And then we can see the differences here, absolute difference potential. So with this red is telling you it's 0.01. So this is 1% if you want to change the percentage difference. So you see there's 1% difference here, and this is above 1%. And this is so because we have some trees also at this side, and then this other way is less. We have below 0 over here too. And then looking at the comparison to for another time, this is another date, 13/12/19. You see the potential difference, 1% and 0. So another one here is 2% difference. And we can see that in front of the wall has the highest, which is that 2%. So this kind of tells us, okay, the green wall is having an effect on that courtyard when you put in the data that I've measured. So this is on another day, 16/2/2021. And then we look at the colors to guide the reading of these charts. We see that this is 1%, yellow is 2, there's no place that is yellow here. So at this date, this is more winter. So you can see that the color changed to like blue, to show that it's colder now during the winter season. So at the end of the day, we also look at the literature, existing literature in other studies that have done for living walls. What do they say about their temperature difference? So when we compare the distance, like the difference, the range of the temperature between the maximum and minimum, you see that this study has a high temperature difference. So comparing the left and the right surfaces of the plant too, we see that there's not much difference in them, the temperature. This was the maroon, the two different colors now, maroon, white, blue, and then see the behavior of the plant. And then this other line here is the list. I think the solar radiation behind the air layer. That's what we're seeing now. Solar radiation at the faces of the plant, and then solar radiation at the air layer to show you that it is shading the air layer. So the left surfaces had the highest radiation. Flat surfaces had lower radiation than the left and right surfaces. Adjacent left concrete surface had the maximum radiation. And we say the shaded brick wall had the minimum radiation. So this is a chart showing that. And so we have this for the solar radiation for different times of the day too. You want to see from morning till, this is 22 is 10 p.m. So from 6:30 a.m. to 10 p.m., this is the solar radiation on the different faces. So for the summary of this study, we said the living wall, modular living wall system had an effect of 1 to 2%, that is 0.01 to 0.02 degrees Celsius on the ambient air temperature. And then in the summer, the maximum surface temperatures were recorded at the concrete wall surface and minimum at the air layer between the two walls. And then for the modules, the flat surfaces had the least irradiation and left surfaces had the highest irradiation. And so we have used the life cycle analysis by Tally software. This Tally software is connected to Revit, and then we use it to make a life cycle analysis, to generate life cycle analysis. And then we use the United States Environmental Agency's waste reduction model called the WORM model, and to yield environmental economic benefits. So the methodology for this industrial symbiosis was to identify the industry's matching needs, characterize the product prototype, and calculate its resource efficiency. So with this, I'll go back to the slides and then continue after this this topic. So this the last thing I'll go on to talk about is the current work. So for the current work, we're looking at machine learning predictions. So when we talked about these system boundaries, we're defining what we want to compare. So once we have these system boundaries, functional units from product extraction and production processes, we analyze them and develop models with the machine learning regression algorithms. We have our findings that will provide methods and evidence for material investigations in academia towards a more sustainable society. So this current research, what we're looking at is wind turbine waste. So if we get the data from wind turbines, it's online, different locations, their numbers and their sizes, and then make a first model from it to know the surface area. We're trying to use a material, this is an orange strand board, to get the data of it to make a model, and then use the students' work. So we had a students' work where they made a 3-bedroom bungalows. So get the surface area that we needed for that building, and then try to see how to match them. So if we decided to reuse this waste from the wind turbines when they go out of their lifespan, because they're supposed to last for 25 years. After 25 years, where do we go? Currently, they are being buried. So can we make them a building material? With this, we can make predictions for the wind turbine rotor surface area. We can make predictions for cumulative global warming potential of repurposing and the number of residential bungalows they can cover. And then we can also report on the environmental and economic impacts of their cradle-to-gate life cycle analysis. So this is showing us the oriented strand board. So this was to keep it simple. We have these rectangles and then place them on the wind turbines. So assuming that this is one face, and then you double it for the two faces by knowing when you know these dimensions. And then we have our student coursework where they have already drawn this in Revit, so we can easily tabulate from these works We can use the quantities tool and wall schedule in Revit, get the average surface area of the OSB required for these 3-bedroom residential buildings to get an average, and then calculate it. So in this conclusion, we have seen that circular economy, industrial symbiosis, embodied energy, life cycle analysis are some of the tools that we can add value to our waste through design. So before calling it a day, I would like to show those 3 tools that I mentioned. So first, we talk about the waste reduction model. So if you go to the epa.gov/WORM, you can see here the WORM tool. So if you click on this WORM tool, you can see they have it in a zip. They have it as an Excel sheet and another. So usually I take the Excel sheet. If you click on the Excel, it will download it for you immediately there. If you click on that tool to open it, it will open as an Excel sheet. And then I'll expand this. So here you can read up what it does, what is the waste reduction model, who should use it, and then the instructions. So all here have been it has been prepared for easy use, where we can make our inputs here. So we have these 2 tables. If you read up here, let me close this so that we can see better. So if we read up at that page, you see you describe your baseline generation and management for the waste materials listed below. If the material is not generated in your community or you do not want to analyze it, leave it blank or enter 0. So whatever material that we want to compare, let's say for instance, I was talking about wood. So if I look out here, I can see mixed plastics, electronics, metals, glass, construction materials. Under that, let's pick something like a wood flooring. So we have to put in the dimensions in terms of tons, landfill. So if you have it in kilograms, convert to tons. So for instance, I'm going to put in 10 here. So click in the space. So first enable editing, because if we don't enable editing, it won't let us type inside. So enable editing and then go to the wood floor and I'll put 10 in here. And then the thing you want to do, you want to make sure that you have the same calculation on the other side. So if we move to number 2, it will ask you to describe the alternative management scenario. I'll get that well. Describe the alternative management scenario for the waste generated in the baseline. Any decrease in generation should be entered in the source reduction column. So we're saying that if we are throwing away the wood before, what do we use it? What do we want to use it as this time? So I want to reduce the zoom now so that we can put in the number. I think the zoom is slowing down the computer. Okay, so this is a fixed, and then I'll try again. So drag it. Yes, okay now. Yeah, so we have this whole chart. I think I've shown this, putting the wood as 10 here. So we have 10 here. And then coming to the alternative scenario, we're saying tons reduced at source, tons recycled, ton landfill. So let's keep this simple and then put in the 10 here. I want to make sure I'm in the right space. This is tires. Okay, wood flooring. Okay. Yeah, so we're reducing our source, we say 10 here, and then enter. So the good thing is, once you put in your weights, it automatically generates the results for you. You have a summary report. So it tells you the amount of empty CO2 that is reduced, gas emissions from alternative waste management scenario to tell you that. It will tell you for production to actually generate a chart for you to give you the results, energy. And then when it gives you the result in the energy savings, if you scroll down to the end, you'll see some notes it's telling you about what it means. It will describe the what you call the scenario for you. And then I'm coming back to this analysis results here to see. Okay, some of the analysis results, there's a table here too. So it gives you a lot of tables, reports. It's something that you take your time to read. As you use it, you will learn about it. Production, to tell you about the summary reports. And then up to wages. So a report in terms of wages. What are you saving in terms of paying or not paying workers, to tell you that in dollars. So that is for the WOM model. The next tool is the EC3 tool. So this is the embodied carbon in construction. So here is a North American products platform. But the good thing is that you can get products, details of how these products were made from all over the world. So a quick example here, we have is showing the map of the world. I want to do an example with steel. So here we're picking a material, pick steel material. And then let's say is it rebar or structural steel. And then we're saying next. If I go to next, then you can pick a geography for, so start from the top, let's start from the top. You can pick any quality of the material that you decide to. So yield, tensile strength, if you have that, you set that in, put the recycled content that was in the material, if you know about that. And then you can set the location for where you're using this material, global, so Africa, Sub-Saharan Africa, Western Africa, and then you can pick Nigeria. Okay. And so when you pick the place and then you click on search, it will create a box plot for you to show how this material that we are picking meets, let's say how it meets the requirements for the baseline for the emissions, how it meets for the TRASI. So let me go back and do something that will show us a box plot. So it's still a picked wire and meshing. Let's go for structural steel, hollow sections, and then search. So we look at more. Search by product description, product EPDs. I want something that will show some, when I was practicing, I saw the box plot. So it's not showing a box plot because it doesn't have any products. It's the data that we put in that will show. So some of the data are not in there. So let me try with aluminum. And then it has automatically said alloy. So we search. Yeah, so we can see the box plots. So some products are here. It's up to us to use these tools. And then when companies are aware of it, they will provide the data that will give us the results. So over here, you can see the baseline, and then you can see where the box plot is showing the carbon emissions that were involved in making these products. So this is helping the companies to be responsible in the sense that we're going to be comparing products along the lines of their carbon emissions. So the last tool here to show you is the climate consultants. So this climate consultancy website here to get it, sbse.org, resources, climate consultants. It says use this. It's a simple to use graphic-based computer program that helps architects, builders, contractor, homeowners, and students understand their local climate. So if you put in your location, you can see this chart that was in one of my slides. And it will tell you, this is for Los Angeles, it will tell you the climate in your area. You can use this to go on to determine the thermal comfort and all that. So different things that will show you ground temperature, dry bulb and relative humidity. You have a wind wheel, you have the psychometric charts, and it will also recommend design strategies for you to meet that thermal comfort. So in this blue here is the thermal, the accepted one. So to tell you the things that are making up the things that if you change, it will affect the thermal comfort. So 15% comfort and sun shading. If you shaded the windows, if you've added a thermal mass, that means to make your wall thicker, it would improve the place by 3.1%. So this kind of guides you in making design choices during the retrofit. So I'll stop at that place now. And then this will expose you also to international conferences You can go and discuss. We had one in Finland discussing no cradle, no grave for circular economy into practice. And then we also in Canada talking about building envelopes, how this material, how sustainable can they be, what are their benefits. So finally, I close up with this quote saying, education is not the learning of facts, but training the mind to think, by Albert Einstein. I say thank you, and I welcome your questions now.